What was I talking about? Oh, okay, yeah. So ultimately, we need to talk to our CPUs, right? So ultimately, whatever we do, we need to get this guy down to zeros and ones. Now we've already decided that we're going to work on that high-level language dealy. Okay, we're not going to use the 2-button keyboard. We're not going to use the low-level languages because we're humans. We're more important than that. Okay, we're not meeting the computer halfway. We're going to work with high-level languages because that allows us to think as closely to the way we already think. We've already covered that we're going to struggle with programming because we're too good at solving problems. But at the very least, we're going to give ourselves a tool where we don't have to change too much, relatively speaking. Okay, so we're going to choose a high-level language. So now, how do we traverse this chasm here in the middle? All right, so we're going to there are two kinds of programming languages. We have compiled and we have interpreted. How many of you have ever heard of a compiler? Heard of a compiler before? Okay. You know what a compiler is? What does that guy do? Okay. So, compiled languages use a tool called a compiler. Okay. So this is software that converts from a high-level language to a low-level language. All right, that's what a compiler is. So it's going to take our high-level language and turn it into a low-level language. Make sense? All right. Now, we also have an option for something called an interpreter. This guy converts from a high-level language to a low-level language. What's the difference? So then I would put the little picture in here. So there's our interpreter. We start with a high-level language. We compile it. It goes to a low-level language. We start with a high-level language. We interpret it. It goes to a low-level language. What's the difference? Now, in real life, if which is faster? Let's say that the Russian president is giving a speech. All right, and I don't speak Russian. All right, Russian president's giving a speech. I don't speak Russian. Which is going to be the faster way for a news agency to deliver the speech to me? If the speech was prior to giving the speech, it was translated into English, and then the news agency read it in real time. Or if the news agency hires an interpreter who listens to the Russian speech and converts it to English and says it again. Which is faster? Having it pre-translated into English or having it translated on the fly? Pre-translated is faster, right? Because when you have an interpreter standing up there, there's a delay. You know, they hear the phrase in Russian and they have to convert the phrase to English and then say it. There's a delay. Now, are both of them ultimately going to give me the correct stuff? Yeah, I'll get the right low-level language. You know, I'll get the right output from that guy. But the difference is a compiler does this prior to runtime. Okay, prior to runtime. So that conversion, when we go to run that program, it has already been compiled. So the movement to get it to zeros and ones can happen more quickly. In an interpreted situation, this happens at runtime. So it's happening on the fly. So when you first run the program, it's being converted right then and there on a per line basis, and then turned into instructions for the CPU. Make sense?
Which one faster?
Compiler. Faster. Slower. Just like in real life. An interpreter would be a slower way for me to get the information than if somebody handed me a piece of paper that already had the English version of the speech on it. Make sense? All right, so these are two different mechanisms for getting to a low-level language. This guy happens before we run the program. This guy happens when we run the program. So then the question would be is, why wouldn't we always use a compiler? Isn't fast good? Well, one would think fast is good, right? But first of all, does every program need to run as fast as possible? Or are computers pretty fast to the point that even an interpreted program is going to feel like it runs instantaneous because our computers are so fast? Only certain applications really, really need to run as fast as possible, right? Only certain things actually are very time sensitive and need every bit of computing horsepower that you have. Most applications, we're not going to notice the difference because our computers are so fast. So, with that in mind, we have to consider why we might use an interpreted language versus a compiled language. Well, compilers are very complex to write. Because what does a compiler do? It's taking your high-level programming language. So you're writing your code in Java or Python or C++, whatever it is, and you're compiling it. It's going to try to turn into the most efficient low-level equivalent. Now, an accurate compiler would convert a high-level language to equivalent low-level code. That is, code that functions, has the same functional output. But that might not be the most efficient version of that low-level code. Okay? So for instance, you tell me to pick up that soda. What keeps you from doing all these weird hand gestures and stuff like that before I finally reach forward and grab it and take a drink? Not the most efficient way of picking up, although it looked beautiful, right? So if our compiler produces a whole bunch of extra stuff, extra steps that aren't necessarily required, but it's how it, maybe it was written in kind of a bad way, let's just say. The quality of that compiler might ultimately affect the efficiency of your output application to the point where it might actually run as slow as an interpreted version or even slower. Now, having said that, compilers have gotten pretty good. So our modern compilers for our popular languages that are compiled languages are very, very, very efficient. Now, if ultimately a compiler is producing low-level code, producing like assembly code, would we ever need to actually modify that assembly code? We're saying it's equivalent. So it's going to take our high-level program, we're going to write our high-level code in Python. Well, Python's an interpreted language, so that's a bad example. Let's say we're going to write it in C#, okay, which is a compiled language. Well, I guess sort of. We're going to write it in C++, definitely a compiled language. We'll talk about that in a little bit. All right, so we'll write it in C++. We know we're going to get a functionally equivalent program. But might there ever be a situation where you might want to go in and modify the low-level code that is produced by that compiler? Even with our compilers today that are really, 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 really good, might there be situations where the code it produces isn't as fast as it could be? This is pretty rare anymore that this would happen, but you see it most often in the gaming industry. See, when we write programs, we're writing them in terms of memory and asking questions and repetition. And a lot of times high-level languages, because of their rules, require us to write something a certain way. And we might have to write a function one way to protect against an error that we know would never happen. Because as humans, we know what kind of input we're going to be sending to that function. All right. Now, maybe you have to ask the question, well, if this value is less than 0, don't do this. But what if we just happen to know that the information that guy's going to receive is never less than 0? Ever. Make sense? Okay. It's kind of like if you live in Jamaica. Okay. Jamaica is a hot place, right? Nice weather. Do you really need to wake up in the morning in Jamaica and wonder if it's going to snow? No, it doesn't snow in Jamaica. So wouldn't you agree that it's a waste of time for you to even ask that question? Is it going to snow today? Do I need my coat? Okay. No, it's hot. Okay, it's going to be hot out there. Grab your rum and let's go. This is a Jamaican thing, right? The rum? Yeah, Jamaicans like their rum. Rum. Alcohol. Rum. Rum. I just got back from a cruise. Every island has their thing. Yeah, they each have their thing. And they want to give you free samples, and they want you to buy it. Then you bring it back on the cruise ship, and the cruise ship confiscates it. They'll give it back to you at the end of your trip. Why? Because they want you spending top dollar on the alcohol on the boat. They don't want you drinking the stuff you bought on the island. You drink that when you get home. All right, so in an example there, if we wrote a high-level program that says, I'm waking up in the morning in Jamaica, the high-level programming language might require us to be thorough and ask that question. How am I going to dress today? Do I need my coat? I might ask, is it going to snow? Now, we all know that that's a ridiculous question to ask if you live in Jamaica. But a high-level language, because how rigid it can be, might require you to ask those questions to make it unambiguous to the compiler. Even though we know that's an impossible input. Make sense? Now, if we're dealing with a video game or something like that as the output, and we want that decision-making to happen as quickly as possible, it might be beneficial to us to say, because this one part of the game is really complex and things are happening really, really, really fast here, we want to minimize the number of questions we're asking. And if there's an extraneous question there, we want to get rid of that. Does that make sense? In those situations, it might benefit us to go in and modify some of that low-level code. Go into the assembly language and take out that question. Make sense? Because we know it's something that's a waste of time to check. Now, we're taking the responsibility upon ourselves that there isn't going to be some freak weather pattern that brings snow to Jamaica. I don't think it's ever snowed in Jamaica. I don't think so. A couple times we've gotten some flurries in like northern Florida or something. Jamaica. You know, it's maybe been like 40 or 50 once, something like that. It doesn't snow there. Okay, we're taking on the risk because we're saying, look, we really should have asked this question, but we don't have to. Because as humans, we happen to know the nature of the data that might be coming into the program, right? But from our high-level languages perspective, they have to write themselves unambiguously. They don't necessarily know what we know. All they can operate off of is like, look, you're saying you're going to give me a string. You're going to give me a number. Well, sometimes numbers, you try to divide them by 0. That's a thing you might try to do, and it's bad news. Now, maybe you say, look, I understand that, but I'm never going to try to divide by 0. The high-level language is going to be like, I don't know that. I don't trust you. It's going to make you do that check. Make sense? So every now and then, there might be a situation where modifying some low-level code is still beneficial in those situations. We're talking rare, especially today, because our compilers are very efficient. So it would really be in a situation like that where, you know, the human being has a lot of inside knowledge about the exact data that program is going to be dealing with. Just happens to know that it doesn't have to work for all kinds of data because it's never going to receive data that looks a certain way. All right, but having said that, compiled languages, those high-level languages that are compiled, rely on a complex compiler. And complex compilers are hard to write and take up a lot of system resources. You know, it's not an easy task. So you'd only want to do that for a language that's built for performance. All right. So when we say that, when would somebody use a compiled language? Let's go back here. A compiled language versus an interpreted language. So compiled languages are languages created for performance. Interpreted languages are languages created for convenience. But given the speed of our computers today, sometimes those are one and the same. You know, our computers are really fast, and an interpreted language is going to feel just as fast as a compiled language for most programs. Okay. So now once we get something down to a low-level language, getting it to zeros and ones isn't a major translation. We have something in the middle here called an assembler. And that guy does the conversion between this instruction and the equivalent instruction in zeros and ones. All right, so humans write this. This power tool does some conversion for us. This power tool further converts it, and ultimately we have the thing running on the CPU. Make sense?
This again, please. Last one you say.
So this guy, the assembler, this is our low-level language, like assembly language. This power tool right here takes this guy and converts it into zeros and ones. But this is a one-to-one relationship with the CPU. So every line of code in assembly is equal to one instruction on the CPU. These are the instructions for the CPU. So this assembler is taking one line here and converting it into one line here.
One we deal with as a programmer.
We deal with this.
High level.
Yeah, this guy right here. So green light, that's us, okay? We deal with that, and then we Secondarily, we'll have to deal with those two. So we'll write something in this and then use one of these two tools to produce this for us.
Either a compiler or compiled language or
Yeah, either of those languages. You can have compiled languages or interpreted languages, both being high-level languages. So as a human being, we're 99% of the time, we're going to work in a high-level language. Then we're going to use one of these two tools, depending on what language we're using, to convert it to a low-level language. Okay? And we said that once in a blue moon, we might have to modify a low-level language. But very, very, very rarely, if ever. The human being does not need to use the assembler. They don't have to use zeros and ones. And they're not in charge of ultimately feeding stuff to the CPU. So human beings are never associating themselves with those. Every now and then, they have to work at this level, but hardly ever. Their sweet spot is right here. Make sense?
Yep.
So as a programmer, we want this. Okay. There are three kinds of programming languages. We have functional, procedural, and object-oriented. All right, so functional languages. I'm not going to spend very much time talking about functional languages. They're kind of the outlier. But functional languages implement themselves in terms of functions. So kind of a famous functional language is a language called Lisp, or Scheme is another functional language. So like an example of a line of code in one of these languages might be the car of the cooter of the list 1, 2, 3, something like that. So here's a function, here's another function, here's an input. So we're applying this function to this input, then we're applying this function to the output of this function. So it's functions being passed into other functions. Those are functional languages. Not very important for us. I'm not going to ask you any questions about them. Okay, so, and as IT professionals, it's going to be very rare that you'll ever have to work with a functional language. Just not really in your, your world, I guess. Now, if you're one of the folks here that when you came into the program, we didn't have the Masters of Computer Science, and you probably would have gone into computer science rather than IT, then functional languages might be your cup of tea. So for example, earlier, I referenced Blade. Blade's working as a full-time programmer. He would have done computer science if we had a master's in CS at the time. Now we do, but he didn't. He was he was done with his master's before we started that, so that wasn't an opportunity. So if you're gonna become a professional programmer, you're gonna run into functional languages at some point. But if you're gonna be an IT professional who does some programming, then you probably will never run into a functional language. It'll always be procedural or object-oriented languages. This is what we're going to focus on here. Now, one thing I like to point out is the difference between IT and computer science. So obviously you're doing a master's degree in information technology, but that program is being offered within the computer science department, right? So what is the difference? What's the difference between a computer scientist and an IT professional? Yeah.
IT professionals, they are responsible to solve problems that happen for the people. They are serving the people. Computer science, they usually don't deal with the people. They usually deal with the software. They writing code.
So you think IT people there isn't a version of an IT professional that doesn't really deal with customers?
IT people,
Yeah.
they are dealing with the customers.
But do you think there's a version that doesn't? Like, let's take the system admin guy who manages all the servers and things like that. He spent it all day back behind server racks and running cables and things like that. Maybe not spending a whole lot of time talking to people, right? He's not the direct interface with the consumer, but he's still an IT professional. I mean, I don't think what you said is inaccurate. I think it's more common for an IT person to work with a customer than a computer science person. But I don't think it's uncommon for a computer science person to work with customers. And at the same time, I don't think it's uncommon for an IT professional to not work with customers. So the way I like to look at it is that computer science and IT are different sides of the same coin. So as a computer science person, about 75% of your time, you are programming. You are creating new software. 25% of the time, you are utilizing things that have already been created. Probably most of that time is using APIs or database systems for your programs to talk to. An IT professional spends about 75% of their time using stuff that's already been created, whether it's server software or various pieces of hardware or printers or whatever. You're using already existing tools and you're solving problems with those. But now 25% of your time is spent creating something new. And this is kind of a common misnomer when it comes to IT stuff. I think pretty often people go into IT because they don't want to go into programming. They view IT as meaning not programming, whereas computer science is programming. Now, the argument I would make is that computer science is not programming. Programming is the tool that a computer scientist uses to solve a lot of their problems, just as programming is the tool that a IT professional uses to solve 25% of their problems. Does that make sense? And I can even take it to the next level. I would say that the types of programs that an IT person has to write might be more complex than the types of problems that the computer science person has to write. And what I mean by that in terms of complexity, it's more complex to write. As a computer science person, because you're sitting behind a desk writing software all day long, there's probably some pretty powerful power tools out there that make your life easier, right? A lot of drag and drop stuff, click here, double click there, hit the little play button to make the thing run. We have a lot of tools that make our lives easier. So fine, we might be writing applications that the final product seems like it's more complex. But the tools that we get to use to create that are easier to use tools. Now the IT professional, you're writing some server script on a Unix server that's underneath the floorboards halfway across campus. You're remoted in with SSH using some 1970s era Unix text editor like VI, typing in your code, compiling it by hand from the command line, not just hitting the play button. You have to know all these system commands. So when you write software as an IT professional, you're not playing in the nice, pretty sandbox that was built for you to do your job every single day. Because only 25% of the time are you having to go into that sandbox. And that sandbox is dirty. That makes sense? So don't view being an IT professional as meaning no programming. Having said that, what will end up happening is some of you will decide, hey, I like programming. This is the type of thing I want to do. Maybe that means you'll spend 25% of your time writing the code. Maybe you end up being like Blade, where he spends 100% of his time writing software. Okay. Now, other people might decide, I suck at programming. It's just not my thing. So what's going to happen? Does that mean you can't function in the IT industry? No, you can still function in the IT industry. Maybe you have other talents. But you're probably not going to be the first one to raise their hand when you get there and somebody needs some software written to solve some problem. You're going to say, that's not really my cup of tea. And you're going to let somebody else who maybe is a little bit more talented in that area step up. That make sense? So you're not screwed without programming in IT, but I would say you are not a fully well-rounded IT professional without programming. It is an important piece of what you will do in your job, and not having that skill set will be a weakness. That makes sense? Okay, but like I said a few minutes ago, as an IT professional, the chances of you using a functional language are as close to zero as possible. So we're just going to forget about it for us. So now, procedural versus object-oriented languages. So procedural languages tend to be monolithic in nature, where all the code is in one giant file or relatively few files and is executed sequentially. So let's talk about a procedural program in terms of an example. So let's say that over here in this table I had a telephone. Everybody in here knows what a telephone looks like? So if I put a telephone in front of you, you would be able to say, yeah, that's a telephone, right? No problem. We got that. All right. But now this is a very special telephone. So for this telephone, it has no casing on it. What's actually over here is a big pile of wires. Big pile of wires. And I tell you, it's a telephone. At first, you don't believe me. You come over, you start messing with the wires, you find the handset. You hear the dial tone, as if those exist anymore, right? Yeah. And in the end, I finally convinced you, yeah, that's a telephone. Didn't look like one. But functionally, that was a telephone, even though it looked like a big pile of wires. Make sense? So in a procedural language, all the details are visible. So out of that pile of wires that are sitting there, if I need to make a phone call, am I going to need to use every one of those wires? Or are there only certain parts of that phone that I'm going to actually have to use in order to make a phone call? Only certain parts, right? Okay, now, so here we got a smartphone here, right? Do we think that there's the equivalent of all those wires inside of here? Little tiny transistors, bunch of soldering stuff, but there's a lot of stuff that some smart person put together inside of here, right? Do you care?
No.
We appreciate it, but do you think you could probably make a phone call on this? Do you need to know about all those wires? No, you need to go to the phone app and dial in a number and hit call. And then you hear the person talking to the other side, right? So functionally, the way we operate on a daily basis is we think about things in terms of objects. And we use those objects in terms of their public interfaces. So if I'm going to use this guy as a telephone, the only part I care about is where I hear stuff, where I speak, and where I dial the number. Everything else is fluff. In fact, everything else I know is important, but I don't want to see it. Right? Would you rather have this or the pile of wires?
Yes.
Yeah, this guy. Like, we can appreciate that it has all those details in there. And we know that if something goes wrong with the phone, we can crack this guy open and try to fix something. Maybe we wouldn't do that, but we know we could. If we had to get to those details, we can. But 99.9% of the time, we don't want to be bothered by that. Okay? Same thing. We look at this back wall in the room here. Do you think there's some wires and stuff inside that wall? Probably some power wires. So I'm looking here. We got some electricity going in there. We got some networking stuff here. So there's probably some wires inside that wall, right? But can we see them from here?
No.
No, but could I go over there with a hammer and punch a hole in the wall and probably find the wires? Yeah, then I have a big mess when I'm done. They're there. But I don't need to have access to them. When they first built this building, they ran all those wires. And then once they tested to make sure all the wires worked, what do? They put the drywall up. So let's hide the wires. Let's hope we never need to get at these again. Make sense? So object-oriented languages hide the details and only expose the public interfaces. Let's leave it at that. All right. So the object-oriented version of a telephone will look like a telephone. Make sense? It'll look like a telephone. Okay. Now, having said that, we want to talk about the evolution of our languages. Wrong slide. All right, now before I do this, I want to add one more slide here. There are two kinds of programming languages. General purpose and domain specific. So some programming languages, in fact, most of the languages that we probably think of as being programming languages are general purpose. They're created for solving a wide range of problems. Now, every now and then, though, you might have a programming language that's only built for solving a very specific problem. So, for instance, let's say you are somebody who repairs dishwashers. All right. Maybe there's a small programming language on the controller board for the dishwasher that allows them to, cycle, cycle certain functions on the dishwasher or something like that. But, the number of magic tricks the dishwasher can do is only a few, right? We're not talking about a general purpose computer. We're talking about something that can fill with water, drain water, and just spray some stuff, right? So very few things it can actually accomplish. So the programming language for programming that type of thing is also going to be a very simple language. But it's probably not going to be the type of language you're then going to turn around and make a video game with. All right? Because it was made for the very specific domain of programming a dishwasher. General purpose languages, like most of our programming languages we consider, are built for solving all kinds of problems. All right? But it is a differentiating factor between programming languages. What languages have we heard of? Let's get a list of programming languages that you've heard of out here. Fortran? Oh man, that's a... Do you know much about Fortran?
Not really.
You just heard the name? Okay. Here's an interesting trivia question I'll ask at a later point in time about Fortran. You have to remind me of it because you don't have enough background information yet. But something about there's one feature that Fortran does not have that most modern programming languages do. It's pretty interesting. All right, so we have Fortran. What else? Python?
Ruby.
Who? Ruby? C? Java? I'll loosely put that down. Okay. Pascal, man, you and the old languages. So tell me, where are you picking these guys up? Where'd you learn Fortran and Pascal?
I think that's the language they use in like Fortran and Pascal. They use it to do some.
Just Nigeria? So a little bit behind the times? Are they?
I mean, well, we use other languages too.
But do you, like in general, would you say that Nigeria is very modern, or does it still use a lot of older technology because that's what's available?
No.
I don't necessarily know. Very modern. Okay. All right, so now we're back to you. Where are you picking up this Fortran and Pascal stuff from?
Yeah, but we still appreciate the old, like in the universities, they still, like the first year, the undergrad, they still take Fortran and
Interesting. Very interesting. Okay. Do you know Pascal was designed to just be a teaching language? It was never written, it was never made to be a language that people actually used. It's just made to teach. And then it actually became very popular. And they released it into a, Microsoft released it into a product. You know what the product was called that Microsoft released? The Pascal syntax. It was a programming language called Delphi, which then became Fox Pro. Heard of Fox Pro? It's all Pascal-based syntax because it was never meant to be a professional development tool, just for teaching. All right, what else? C++. Who? C Sharp? .NET? .NET is an API. Yeah, when we talk about the Microsoft versus the Apple languages, which will be tonight, that'll make more sense. But yeah, it's an important piece of that, but it really is an API. Okay, what else? R. Ooh, Java-based language.
MATLAB.
Who?
MATLAB.
MATLAB. Actually, that's a functional language. So I mentioned we would never deal with functional languages. MATLAB would be one. So is Mathematica's programming language. So I'll leave it off here just for whatever, but you're not incorrect. Anything else? Who? Perl. Okay, yeah. That guy, yep.
SQL.
Ah, finally somebody took the bait. Not a programming language.
COBOL.
COBOL is a programming language. Here, I'm gonna go ahead just to speed things up a little bit. I'm gonna throw another not programming language in there. Okay, so and actually let me specify here. These are programming languages. So I mentioned SQL and HTML, not programming languages. What about XML? Oh, it's not showing up on there. What about JSON?
JSON not.
It's a notation.
Like XML.
All right, so I'm going to come all the way back up here. We asked, how do humans solve problems? We said memory, asking question, and repetition, right?
Yeah.
The very next slide, I like to call this one the mapping. And I'm going to steal these three things. So every programming language will have a facility for emulating memory. Usually it's through something called variables. Every programming language will have a facility for emulating asking questions. These are typically called conditionals, if statements. We'll talk about why it's usually an if statement in a few minutes. And they will have facilities for emulating repetition through loops and functions. Functions slash procedures slash methods slash subroutines. We're going to keep it old school. All right. 100% of programming languages will have facilities for these three things. Because the job of a programming language is to allow us to solve problems in a very similar way to how we already solve problems and ultimately tell a computer what to do. And because this is the way we solve problems, for a programming language to do its job, it's going to have to give us tools for emulating those things. That make sense? All right. SQL does not allow us to define variables, doesn't allow us to do conditionals, and it doesn't allow repetition. Instead, SQL is a data representation language. Okay, it's a query language that we're using to talk to typically relational databases, but now it's even a little bit beyond relational databases. So I'm going to throw another thing out here. So pretty often, this class didn't really fall for it, but pretty often I'll say, oh, what programming languages have you had? One of the first ones that gets thrown out there is HTML. It's like, oh yeah, I've done HTML. HTML is not a programming language. You can't define variables. You don't have conditionals. You can't write functions. You don't have loops. Now let's think about something for a second. What is HTML language? What is HTML used for? Web page stuff, right? It's web page stuff. So let's look at what that model looks like. So we have something called a web server, right? Then over on this side, we have a web client. What's a web client? Browser. So the web client is our web browser. Okay? And these guys talk, and who's the client of the web browser? User, person. So here's us. We talk to the web browser. The web browser then talks to the web server on our behalf. Now, what language do these guys use to talk to each other? Think PHP?
They use HTML.
They exchange HTML with each other, but that's not the language they use to talk with each other. So right now, we're using English, right? Okay. Even though many of you speak languages other than English, we've agreed against your will that that's the language I speak, right? I'm also fluent in Urdu and Telugu. At least that's what I tell all my Indian students. I don't speak either of those. Do any of you know Shiva? I was on the phone with Shiva's dad last night. He doesn't speak any English. He speaks Telugu. So I was, of course, speaking Telugu to him. And he didn't understand a word. It must have been my accent. Didn't understand a word I was saying. But, yeah, so they keep trying to teach me some of the, I don't know, dumb American. Never going to learn it. Yeah, so these guys, we're speaking English, right? These two guys need to have to agree upon a language to speak with each other. Now, in the technology world, we have a synonym for the word language, something that means the same as language that's commonly used in technology. Anybody know what that is? Mm-mm. A protocol. Protocol. So in technology, when somebody says protocols, they're really talking about the language that two systems use to talk to each other. All right? Huh? Yeah. Right now, we're using the English protocol. Make sense? It sounds weird to say it like that, but that's what we're doing. So we say language because it sounds more human. Right? But we really agreed upon a set of rules for us to communicate. And we're following the rules associated with the English language. Make sense? Okay, so, but in technology, we don't, instead of saying language, when we talk about two things talking to each other, we call them protocols. These are already established. You could even think of a protocol as being kind of a domain-specific language. Okay? It doesn't have to solve all the world's problems. All it has to do is allow two things to say all the things they need to say to each other. Make sense? Okay, so we're going to see that the protocol that a web browser and a web server speak is actually a pretty simple protocol. but it's also pretty fascinating. It's something you see today. So does anybody happen to know what the languages these guys talk? HTTP. HTTP, good. Yeah, so these guys are speaking HTTP, Hypertext Transport Protocol. Doesn't matter if you know what it stands for, just this is the language that these two dudes use to talk to each other to agree upon what's going on. Okay? Now, along the lines of what you said, the web server will always spit back to the web browser HTML and JavaScript. Its response will always contain that. All right? Because that's the thing that this dude knows how to work with. That's the kind of data he requires. Make sense? Now, why JavaScript? Well, it's only a little bit object-oriented, but first of all, is JavaScript a programming language? Forget about that. Does JavaScript belong on our, where's our list? Here? Well, does it belong there? Yeah, we put it just because you said it, right? Does it belong there?
I think it does, because we can save stuff. We can assign memory.
Are you willing to bet your grade on this?
No.
What kind of confidence is that?
That's $2,000 down. I'm not gonna bet that.
Well, I mean, you can buy back in. It's like buying new chips at the casino. It's a programming language, yeah. JavaScript allows you to create memory, variables and stuff, ask questions, repetition, blah, blah, blah.
We use it to do dynamic update.
Ah, we do.
Yeah.
Why? Because that guy can't.
Yeah.
HTML can't do that stuff. So if you want to do logic stuff, you need JavaScript. Right? Okay, so the web server, no matter what it does, will always spit back HTML and JavaScript. All right? Now, earlier you mentioned something like PHP. Right? So I'm going to, actually let me, well, I'm already halfway down the path. Let's just do web languages first then. So at the end of the day, the web server is just managing a directory of files. So we might have index.html and user.php. Let's just say those are the two files that's on that server. Okay, so if the web browser makes a request, so let's jump up here real quick. So HTTP. Anybody know what the functions are in the HTTP Hypertext Transport Protocol? What are all the words in that language? You're on the right track.
Send response.
So she said get,
Get.
post, she's already got a star for the day because this is way better than most. One short. Starts with a P. 3 letters. What? So HTTP has been around since the beginning of the internet, right? Been around for a long time. And it has these 4 functions. But the reality is we've pretty much only used 2 of them for a really, really, really long time. We use gets and posts. So what we might have here is we might say get index.html. So the web browser requests from the web server to get index.html. So the web server receives that request, says, okay, let me look. It finds index.html. Now, how many of you have heard of something called a MIME type? Anybody hear of a MIME type before? Anybody know what it means? One thing we run into in technology, and hopefully you have an appreciation for this, is more times than not, we have really fancy words that mean easy things, right? Because it lets us sound smarter. So what's a MIME type? A MIME type is what kind of program should this file be opened with? So we look at the MIME type of this guy. He ends in .html, so we look at the suffix, the extension. It says that HTML, its MIME type is text/HTML. So the web server gets this request, it looks at the file, finds the file, says, what is the MIME type? The MIME type is text HTML. And then the web server goes, woot! It's already in the format that my requester expects, because he's expecting HTML and JavaScript. So what does he do? He just spits it back out. He just takes the contents of that file and spits it back to the web browser. The web browser converts it into pretty pictures and text, right? What happens if we asked for user.php? PHP, we mentioned, is a programming language, right? So the MIME type for that guy is not going to be plain HTML. The MIME type for that guy is a PHP application. And we presume the output of that program will be HTML and JavaScript. So what do we have to do before we can spit back an answer? To run that program, right? The web server is going to have to say, before I can give you an answer, I got to execute this program with any inputs you may have given me, and then I'll spit back the resulting HTML and JavaScript. So it has to do some additional processing. That make sense? Okay. So what are the possible languages that we might have over here on the website? So I'm going to kind of go back over here for a second, and I'm going to leave C up there as my starting point, because when I teach this stuff, I like to teach it from some sort of starting point, and I like to pick C as kind of, let's call it the first programming language. It's not the first programming language, but let's just say it's the first one that modern programming cares about. Okay, so and we're going to have two sides to this little chart here. The right side, this guy over here, is going to be our desktop native languages. So we're going to pause on that for a minute, and we're going to go over here and we're going to talk about our web languages for a little bit. And the first one we're going to put over there, and you get a star for the day too, because typically people don't come up with Perl. That's a programming language. So the first one I'm going to put there is going to be Perl. Now, where's your star, Promise? Actually, wait. We got Fortran and Pascal from you. That's star worthy. That's star worthy. Most people don't know about those. That's impressive, actually. I mean, now you've raised the bar. That might be dangerous.
You mean server-side scripting?
Yeah, I'm talking about server-side languages.
ASP.
Yeah, we'll get there, but you're right. You're right. So Perl is a programming language that came from C. So it was based on C. So it looks like C. It actually is an interpreted language. And Perl actually predates the internet. So who used Perl? What kind of person would have used Perl as a programming language? Probably IT professionals. Earlier we kind of mentioned that about 25% of your job as an IT professional might be programming. That's probably mostly the Unix system administrators. So as a Unix system administrator, Perl was kind of your go-to tool. I mean, kind of what came before Perl would be shell scripting. So you might write a C shell script, or just a shell script, SH, or a bash shell script if you work in Linux. But Perl was kind of a common language that a lot of Unix system administrators used for doing their automatic backups, account creation, stuff like that. This language was in existence before the internet was in existence. Right? That doesn't mean it's ancient. The internet hasn't been around that long. I mean, we're talking, early 90s or something like that until the internet was kind of a thing. And really probably 94 or 5 was when the, probably 1995 was when people were really almost using the internet. Like it was kind of a term that people were aware of. 505. Yeah, and some of you might not have been a thing then. How many of you were around in 1995? 1.5 people were around in 1995. You were around in 1995? Promise? What year were you born?
1986.
Really?
Yeah.
Man, you look young for your age. That's impressive. 86. Man, I mean, that's almost going back far enough when the Bears last won a Super Bowl.
Is he close to your age?
The who?
Is he close to your age?
Is he close to my age? No, I'm older. By a couple of minutes. Yeah. Yeah, a couple of minutes older. I've been teaching for 18 years.
I've been teaching for 10 years.
Yeah, I'm old. How old are you?
Me, 35.
34. He's almost 35.
No.
Almost. All right. So Perl predated those languages. It's really something that's used by Unix system administrators. But now what's interesting about Perl and why I keep it on this list for our web languages is because the internet became a thing while Perl was still very popular. So what you had is you had this new thing, this new internet. And today we take it for granted, right? The internet is something that's it's always been here. Right? So for most of you, not you. I mean, do you remember before? No, I mean, do you remember before the internet?
Yeah, sure.
You remember it, right?
Sure.
I mean, you were young. You were young, but you remember.
Yeah, I remember.
Man. And before cell phones? Man, when friends would come over and knock on your door or ring the doorbell and say, "Can Mike come out to play?"
Yeah.
And now what happens? Somebody knocks on your door, you start hiding. Like, who's at the door? Why didn't they announce themselves via text, right? So, but in any case, in the early days of the internet, when they didn't necessarily know whether it was going to be the next big thing, because universities were kind of the first place that the internet was sort of kind of becoming a thing, and a lot of businesses started having, at least in the early days, websites, right? That was what the cool kids did, is they had websites. The Unix system administrators were put in a position where they had to support something they really didn't understand, right? They had to run a web server, so they were probably running like Apache on a Unix machine, and then they had to have a way of doing server-side stuff. So when we had this picture back here, we said that, okay, well, this guy requested user.php. In the old days, it probably wouldn't have been user.php. It would have been like user.c, okay, or user.cgi. CGI was Common Gateway Interface, okay? And that guy so it had to come over here, and it then had to execute that program. Now, back then, these things weren't as integrated. Now you bring up a web server, it pretty much supports PHP out of the box. Okay, supports a couple of things right out of the box. If you want to have it support Ruby, maybe it's like a quick module you add on. These things are made to quickly support a lot of different technologies. Back then, those technologies didn't exist. You wanted to have some sort of server-side stuff. You had to do quite a bit of web server configuration to get that to work. Make sense? All right, so that's where kind of CGI came in. So in the early days here, the Unix system administrators had to use Perl to kind of allow them to pull off internet-y type stuff. So a lot of those early server-side scripts for like processing logins or account creation stuff, whatever, was actually programs written in Perl, not things like PHP or Ruby or stuff like that. So it was written in Perl. Now, I may be skipping some languages here that are along the evolutionary chain, if you will, but this kind of takes us on that path that gets us where we are today. PHP was really the first language specifically built for the internet. You know, it's got functions built in it that consider what people want to do for server-side stuff. Make sense? All right, now, so we already kind of mentioned like weaknesses with Perl. Perl was never designed for an internet thing, right? So we say PHP here. PHP was designed for the internet. Now, do you think websites today are more complex than what websites were in the early days of the internet? Sure, by a lot, right? I mean, now you got your web pages have stuff dancing all over them and things like that, but you know, in the early days, it was basically a picture and some text, not a whole lot of stuff going on. And would you say that the design of web pages, not just the content that's on them, but also the way they look is far more complex today, right? So a weakness, well, let me throw another thing up here. How many of you have heard of something called the design pattern? What is a design pattern? Anybody know? Kind of invented by academics. Heard the phrase "publish or perish" before? So for academics, we're supposed to do research papers and stuff like that and get them published because it makes us look better, right? That's kind of the punchline. Well, the computer science people decide, you know what? There's all sorts of things that people try. Because I mean, when you do research doesn't necessarily mean solving new problems. Researching could also mean pointing out bad solutions to problems. Like, hey, I tried this, it doesn't work. You know, like making a peanut butter and jelly underwater. You probably wouldn't do that. It doesn't work right. Right, Promise? You eat peanut butter and jellies? You like peanut butter and jelly, don't you? Not really? Really? It's weird. What? If you're hungry, well, anybody would eat it if you're hungry enough, unless you have like a peanut allergy. Yeah. But in any case, you probably wouldn't make those underwater. Kind of bad. It would be a bad place to make a peanut butter and jelly. Right? You know, same thing, you probably wouldn't drink hot tea when it's 105 degrees outside. You want ice water or something cold. Right? Well, so what design patterns are is, first of all, they need to have a funky name. So a design pattern is a proposed, I'm going to put it in quotes, good solution to a common problem. Okay? Notice I have in quotes good and common. What does it mean for a solution to a problem to be good? What does it mean for a problem to be common? Okay, so using the peanut butter and jelly as an example, you know, there's probably 3 or 4 different ways that somebody can make a peanut butter jelly and they think that's the best way. You know, maybe you put the peanut butter on first on one piece of bread, and you put the jelly on another piece of bread, and you put them together. Okay, or maybe you put the peanut butter on first, and you kind of put the jelly on top of the peanut butter, then put the other thing on top. You know, whatever it is. You know, you have some different approaches to it. And you could argue that your way is a little bit better than somebody else's way, but at the end of the day, they're all accurate ways of making a peanut butter and jelly. Okay? And that might be a common problem for people who eat peanut butter and jellies. Okay? Well, if you work for Lockheed Martin or something like that, a common problem might be missile tracking or something, right? You know, you solve all sorts of different kinds of problems. So design patterns are very flexible. And now, so you literally have millions of different design patterns that are out there, most of which are kind of jokes, right? It's academics decide that, okay, well, here's a good solution to solve this problem. And it might be an okay solution. It might be a mediocre at best solution to solve a problem. You submit it to some journal, it gets published, you count it as a publication. Somebody else reads the paper, says, yeah, that would work, but here's a better solution. And then you say, yeah, you're right. I agree. You've still advanced research. You've said, here's a bad solution to it. Okay, you can make a peanut butter and jelly underwater, but it might not be the best way of going about it. Okay, but you can do it. But you still got your publication, and as long as you attach a funny name to it, it's a design pattern. Now, every now and then, some good design patterns come out of the hodgepodge. And a famous one that we're going to talk about here is something called MVC. How many of you have heard of MVC before? We've seen it printed somewhere or something like that. Anybody know what it means? Model view controller. All right, so far so good. Now what does it mean? What problem is it solving, and what's the solution? So it has a funky name, right? So we're good there. It passes the test for design patterns. Okay. And does its name sound like something that a smart person probably came up with? Sounds legit enough. But based on what I said earlier, most hard-sounding problems or hard-sounding words typically mean easy things, right? Model view controller says it's a good idea to separate your design from your logic and your data. Okay, it says it's a good idea to separate your design from your logic and your data. So if you're making a web page, what would make the most sense is to have the way your web page looks here, to have the logic associated with how your page works over here. And then if you have a database somewhere, have that over here. Not all in the same file. Make sense? So, PHP did not support MVC. Now, the good news for PHP, I guess, is, first of all, in the early days of PHP, this wasn't a big deal. When you look at a PHP document, the file extension is .php, but inside the document, you see a mixture of HTML and PHP code, i.e. you've broken the MVC rules. You've mixed your logic and your design. The HTML is the design side, the PHP is the logic side, bad news bears, right? You probably also have some JavaScript mixed in there as well, which just really adds to the excitement. Now, if you're writing a pretty simple website, is that a big deal? Got a couple of lines mixed together, no big deal. But as sites got more and more complex, all of a sudden it becomes a disaster. When you look at that PHP file, you got 700 lines of gibberish. And to debug anything in there is difficult. Okay? So really what we needed is a solution to this problem. Now, many of you might know that PHP is actually still popular today. So luckily, we have had some good solutions pop up that have allowed PHP to still stay relevant. One of the other weaknesses of PHP early on was that it required an IT professional whatever, to bring up a compatible web server. That is a web server that had the PHP module on it that could pre-process PHP code. So how's that been fixed today? Well, you can go to GoDaddy, and for $5 a month, you can get a Apache server that already has PHP support, and you're good to go. No big deal. So you don't have to be an IT professional in order to do PHP stuff, as long as you're willing to give $5 a month to GoDaddy. Similarly, MVC is now supported through some template tools that allow you to design and then call that inside your PHP program. So we've got some third-party applications that have kept PHP alive, and it's still fairly popular today. But back then, we didn't really have that much of that stuff. We needed to have kind of an upgrade to it. I'm going to throw my next language on here, and then we'll take a little break. So the next language that came out was a language called Ruby. All right, so let's take 10 minutes, then we'll come back and we'll finish off the last hour.